Guys, here we go. Section 6.1, we're talking about function composition. Or composite functions. Same thing. Function composition resulting in what's called composite functions. So with function composition, one of the things that we need to make sure we know how to do is function value. Say we had f of x is equal to 6x minus 7, and they ask us to find f of negative 3. What does that mean do? Yeah, just replace the x with a negative 3 and follow order of operations to simplify that. Be negative 18 minus 7, and then be negative 25. So that gets us that function value. Also creates an ordered pair if we needed that of negative 3, negative 25, x and y. But function value, you got to know what that means to deal with that. So if we don't know what function value is, we could run into some problems. Even same idea. They ask us for g of x being 3x over x minus 5, find g of positive 4, something like that. What do we do with the 4? Plug it in. Just one spot or every spot? Every spot. Be careful of that don't forget. Hey, that 4 goes in that other x area as well. 3 times 4 is 12. 4 minus 5 is negative 1, so that ends up being negative 12. So g of 4 is negative 12. Function value. Really easy thing, but important as a basis for composite functions. All right, so let's define some function composition. Function composition is f composed with g. That is an open circle there. It's not the word fog. It's f composed with g. Means take the g of x function and use it as the domain of the f of x function. Plug the g of x function in for x in the f of x function. So whatever function is listed second, in this case g, goes into the one that's listed first. Okay? Second one into the first one. Okay? And we need to talk about the domain of those because that's an important skill in here. It's a set of all numbers, in our case x, in the domain of, in our case, g of x. That's the second function. Such that g of x is in the domain of f of x. First function. And when I say g of x there, I'm referring to the y values that go along with that domain. So be careful of that. So the y values of the second function become the x values of the first function. That's really what's happening here. All right, so let's work on some domain of composite functions and building some composite functions here. So example C is we're gonna get f of x 2x squared minus 3 and g of x, just simple, something pretty simple, 4x. And they want us to find f composed of g of x and the domain. Okay, so f composed with g of x means take g of x and put it in function value style in f of x. Okay? So we don't have a number there, but we've got a function that we're going to put in there. So we're going to take this and replace x with it in that function. That's what function composition does. So we got 2 parentheses 4x, and then that x was squared, so we put a squared on the parentheses there, minus 3, and then simplify that as much as you can. So 4 squared is 16, x squared is x squared, and then we're doubling that to get 32x squared minus 3. That's what f composed with g of x is. So there's our function, our composite function. And then we need to look at our domain of that. And when you're looking at domain of composite functions, you really need to look at the domain of your two functions that were used to make the composite function. So the building parts of that. So if I get the domain of f of x, what's the domain of f of x? Are there any red flags that come up there? No, there's no square roots. There's no x in the denominator. So the domain of f of x, and I'll put an equal sign there, I'm in a colon, would be all real numbers, or from negative infinity to positive infinity. That may be a good way to put that. And then on g of x, there are no restrictions either. No red flags. X wasn't in the denominator. X wasn't in a square root, so we didn't have any issues there. So with the domain of the composite function, if there are no restrictions on either of the original ones, can there be any restrictions on the composite? Absolutely not. Not going to happen. Okay. All right. F composed of G, and then it would be, since there's no restrictions on the other two, those two don't. That composite function doesn't have any restrictions on it. And we'll see some as we go along here that do have some restrictions, and we'll learn what to do. Okay. And then you could take that and do function value with that composite function if they ask us, as you know, maybe our next example, D says find f composed with g of 2. That means you're just going to take 2 and work it in that problem. So that seems very basic, but I feel like I should always cover that. 32 times 4 minus 3. 128 minus 3, 125. So getting the composite function and then plugging in the number. Another way you could do that would be find g of 2. And like if you went back to the original function, g of 2 would be 2 times 4, and that's 8, and then find f of 8. That's a way to get that function value without doing the actual composite function. Is to go one step at a time, like go into the second function, get its answer, take that answer and plug it into the first function. If it's only asking for function value, you could end up saving yourself a lot of algebra work for the composite function. If you don't need the composite function, you just need the function value, you could get there and still get 125 out of that. That if you did it that way. That's where that 8's going. So that's just an alternative to that. Let's look at a couple of much different functions to do composition with. Example E, f of x, 1 over x plus 5, and g of x, 4 over x minus 1. Very much different because you got lots more going on. So if you're going to do f composed with g of x, we're taking the g of x function and replacing x in that function. So a little bit of challenging algebra here, because adding a fraction with an x minus 1 on the denominator is not exactly native to us, but it works the same way. You got to have a common denominator. X minus 1 is that denominator. The 5 was over 1. It needs x minus 1, so the top gets x minus 1 is 2. So I'm trying to do step by step on that as to why you're doing it that way. And then that allows us to then add those two fractions on the bottom, because we got 1 over 4 plus 5x minus 5. All of that is over x minus 1. And that'll simplify a little bit. 4 and negative 5 are like terms, so that's 5x minus 1 over x minus 1. But that's a fraction inside of a fraction, and that's never allowed in math. You don't do that. So dividing by a fraction is the same as what? Multiplying by the reciprocal. So dividing by 5x minus 1 over x minus 1 is the same thing as saying 1 times x minus 1 over 5x minus 1. Reciprocal. And then 1 times that just gets you that back. And there's our composite function. Good deal of work to get there. But definitely something, worth seeing there. All right. So let's look at the domain of those. Let's get the domain of f of x. F of x was the original one was 1 over x plus 5. What's the restriction on that? X can't be negative 5, right? And the domain of g of x x can't be how much? Positive 1? Yeah. All right, so those are the restrictions on those two. Now, here's what we've got to look at is we're taking the g of x function and putting it into f of x function. We're taking the y values. The g of x is the y values for that. So when is the y value for g of x the same as that restriction on f of x? That's what we've got to find. So when is 4 over x minus 1 equal to negative 5? Okay, so when is the second function equal to the restriction from the first function? That's kind of the general idea that we're looking at here. Specifically on this one, when is that 4 over x minus 1 equal to negative 5? And we need to solve that problem. So it's an equation, can be solved like any other equation. This one I'm going to set it up and do like a proportion because it's easier to do that way, right? You just cross multiply. So that'd be 4, and this side would be 5x minus 5, and then add 5. 9 equals 5x. Right? That's a negative 5, so that'd be plus 5. Sorry. Thank you. You caught it before I did. So subtract 5. So that'd be negative 1. That's better. And then divide by 5. So the restriction is x can't be negative 1/5 for that composite idea. All right. So the restrictions when you go to do your domain of your composite function, f composed of g of x. Okay. Your restrictions are x can't be Negative 1/5. That's the one. That's that guy right there. But there's another restriction it can't be. It comes from what was the restriction on the original one we're plugging in, the g of x function, the second function. What's its restriction? It was 1. So it can't be negative 1/5 or 1. So there's the set notation for that. That's really easy. The interval notation, a little less easy, but still doable. From negative infinity to, that would be, let me get our signs right, positive 1/5, not negative 1/5. Sorry about that, guys. Scrambling to get in a hurry here. And I shouldn't be. Get to what we get to, and what we don't, we'll get next week. Sorry about that. That should be a positive 1/5 on the restriction, not a negative 1/5. Positive 1/5 and positive 1. So we go negative infinity up to positive 1/5, union with 1/5 to 1, union that with 1 to infinity for the interval notation for that. Obviously, set builder is much quicker and shorter and prettier, but the interval notation still need to be able to bounce back and forth between those two as we go. So when you're looking at restrictions on domains of composite functions, you got the restriction from the second function, and then the restriction of when is that second function equal to the restriction of the first function. Those are the things you need to realize there. So restriction on second function and when is the second function equal to the restriction on the first function. And that's in your composition statement, the order that's listed in. Okay. If there's no restriction on the first function, then you don't have to worry about doing that. It would only be the restriction on the second function. If there's no restriction on the second function, but there is a restriction on the first function, you still have to do that equation work that we did. But you won't have as much stuff in your interval notation and your domain to worry about. Let's look at another one just to make sure we're kind of hitting that. What are we on? F? Is that right? Yeah. Example F. F of x is the square root of x plus 3. The plus 3 is inside of the square root. G of x is 2x plus 5. Okay, and then we want to find the composition F composed with G of x. So let's find our composition first. What are we plugging in where? All right, so 2x plus 5 and then plus 3. Simplify if possible. We got a couple of like terms there, so 2x plus 8. And then you would kind of try to look to see if there was anything that you could factor out of that would have a square root. 2 is the only thing that factors out. 2 doesn't have a nice square root, so we don't do it. If they were both divisible by 4 or 9, 16, 25, something like that, then you get something working nice for you. But for this one, nothing happens there, so it works out good. And then we want to find the domain. So we need to find the domain of each piece. And then get the domain of the composite function. So what's the domain of f of x? How do we find it when it's a square root? Take what's under the square root and set it greater than or equal to 0. And find that amount. So x has got to be greater than or equal to -3. Are there any restrictions on g of x? No, it's negative infinity to positive infinity. Okay. Now, because there are no restrictions on g of x, we get kind of we don't have quite as much to list, but we do have to worry about the restriction from the first function. So when is the second function fitting that? So we've got to make sure that that's happening. So we set up g of x. When is it greater than or equal to negative 3? So when is g of x greater than or equal to negative 3? And that's coming from this. That's where that's coming from. So you set that up, 2x plus 5 greater than or equal to negative 3. Okay. And then subtract 5, 2x greater than or equal to negative 8, divided by 2. X has got to be greater than or equal to negative 4. Okay. So our restrictions for our composite function, the domain for that, restrictions from your second function listed. Are there any restrictions from the second function? No, so we don't have to worry about that. Then the restrictions from this work we did here. That restriction is that x is greater than or equal to negative 4. Okay. And then let's write it in interval notation. Bracket negative 4 to infinity. That's our stuff. Not too bad. But process over and over there. Let's look at one that's a little bit more involved. Maybe we got some fraction work in there, some factoring stuff to do. So example G. Say we got h of x is x squared minus 5x plus 7, and then k of x is 3x over x minus 2. And we want to get the function h composed with k of x, get that composite function. So this one's a little ugly because you got a fraction that you're plugging in to another function. So we're replacing x with this big ugly fraction here. So that's 3x over x minus 2, and we're squaring it. And 5 on 3x over x minus 2, and then plus 7. Little rational equation work here. If I square a fraction, that means I square the top and the bottom. So that's going to give me 9x squared up top. On the bottom, I'm just going to write it as x minus 2 squared, because it's not going to really help me to multiply it out and make a trinomial out of it. And then on the next piece, that'd be negative 15x over x minus 2, and then 7. Well, in order to add those things, and it's much easier to find the domain when it's one big fraction instead of 3 separate pieces. So let's make it into one fraction. The common denominator for that would be x minus 2 squared, because this one has one of them, that one has 2, and that's really over 1. So we want to get the common denominator to be x minus 2 squared. So this guy needs an x minus 2, and this guy needs x minus 2 squared to make it work. So that means their denominator is going to be x minus 2 squared. And then we got 9x squared. Then I'm going to multiply negative 15x times x minus 2. So it'd be negative 15x squared plus 30x. And then over here, I got to do a little bit of side work here. That x minus 2 squared, x minus 2 squared would be x squared minus 4x plus 4. And then distribute a 7 to it. Yeah, it's pretty ugly, but we can make it look a little bit better by simplifying. 9x squared, positive 7x squared, 16x squared. Whoop, hold up, we got 15x squared too. Negative 15x squared, positive 9, and then positive 7. So that'd be 1x squared. And then we have 30 and negative 28. That's 2x, and then the plus 28 on it again. And then x minus 2 squared. There is our composite function, h composed with k of x. Ugly, ugly, ugly. A lot of algebra involved there. Common denominator is the key, though. All right. Now, for the domains, domain of, h of x, are there any restrictions for h of x? No, none. So it's negative infinity and positive infinity, which is nice because that means we don't have to worry about doing that equation work stuff. So the only restrictions for our whole problem are going to be coming from the second function, the domain of k of x. What's the only restriction for k of x? Yeah, x can't be positive 2. Look at the denominator on our composite function. What's the only thing that would mess it up? Positive 2, same thing. Even though that's a squared piece in the bottom, it's the same piece squared. So it only counts for that. Okay? And then, so we're going to take our domain of the composite function, h composed with k, and that's going to be, x such that x cannot equal 2. Curly braces don't look too good today. And then that would be from negative infinity to 2 to infinity. There we have it. Okay. Sorry. There we go. All right. So function composition. Doing lots of stuff there. But got to keep in mind about your restrictions for the domain stuff. That's really what you got to look out for. All right. Let's look at section 6.2. One-to-one functions. And inverses. One-to-one functions. Map 1x to 1y. Thus the term one-to-one. Okay. In this case, a function, remember, it can't repeat x values, but a one-to-one function doesn't repeat x values or y values. So there's the difference in the two. One-to-one can't repeat, no repeating of x or y values. That's kind of the gist of that. Okay. So to determine if something's one-to-one, you look to make sure nothing has been repeated, period. Nothing at all. So no x is repeated, no y is repeated. If they give you a set of ordered pairs, you look at the ordered pairs. Did they repeat an x? Not one-to-one. It's not even a function. Did they repeat y's? Not one-to-one. It may be a function, it just may not be one-to-one. So you got to look at that sort of things. The kind of the test that you can use when you don't have a list is the horizontal line test. Horizontal line test can be used to determine if it is a one-to-one function. Before you even get to the horizontal line test, you got to check the vertical line test to make sure it's even a function. Okay, so vertical line test comes first. You determine something is a function, and then you decide, okay, is it a one-to-one function? And you use the horizontal line test. The horizontal line test works the same way as the vertical line test does. It's just horizontal. So like you've got this graph, something like that. And if you can draw a horizontal line that hits that more than once, there's two spots where that touches, infinite number of possibilities of that happening, then it's not one-to-one. What that's going to lead to is if it's not one-to-one, then you can't have an inverse function. I mean, it doesn't have an inverse, it just doesn't have an inverse function. So if it's not one-to-one, it can't have an inverse function. Another example, just a sketch of a graph. Something real simple like that. Nice polynomial could do that. If I drop a horizontal line anywhere on that, it only touches it in one spot everywhere I put it. So that passes the horizontal line test. It also passes the vertical line test. So that is a one-to-one function. Horizontal line test passes that. If you get an equation, same thing can happen. If they give you f of x is equal to 3x squared minus 5x plus 7, is that a one-to-one function? Why not? It's quadratic, and we know quadratics look like that, right? And that would definitely fail the horizontal line test. Where you've got to be careful, though, is if they give you something like this, like 2x to the third plus x minus 4. It's cubic. So sometimes, like example B could be a cubic equation. It may not necessarily be one-to-one, though. And you gotta look at the graph. So you'd pull out your graphing calculator and you'd graph that equation and see if it would pass the horizontal line test. And depending on what stuff is in the middle there, the 2x cubed, the plus x, that changes things. So here we got 2x to the third. Was it plus x minus 4? So does that pass the horizontal line test? So that is a one-to-one function. So you gotta look at those graphs. If that were x squared in there in the middle, I change that. That would not pass the horizontal line test. There's a flat spot there that it goes through. So that would not pass the horizontal line test. Not necessarily. There's not a rule that you go by there that if it's got a squared term, it'll always not be. That doesn't necessarily always hold. You want to just graph it and check it. That's the quickest and easiest thing to do there. Graph it and check it. All right. So inverse functions. What are they? So here we've decided what one-to-one functions do. Let's talk about inverse functions. Inverse functions interchange the domain and range. Okay. They swap x and y, basically, is what you want to remember. Inverse functions swap x and y. We're going to find the inverse of a function. Let's say we have a function. What letter are we on here? And it's a list of ordered pairs. We'll start with something real simple like that. 6, -3, 7, -1, 13, 2, -8, 5. All right. The inverse, and the way you note inverse with functions is like with the little -1 exponent. You read that F inverse of x. It looks like a little -1 exponent in there. That's F inverse. Swap the x and y values. That's what you're doing. So the first ordered pair changes to -3, 6. The second ordered pair, -1, 7, 2, 13, 5, -8. And that's the inverse function. Got to be 1-to-1 to find an inverse function. Okay. So inverse functions always swap x and y. It's got to be a 1-to-1 function for you to find the inverse function, though. Okay, so that's always has to be 1-to-1 to have an inverse function. Yes, ma'am. That's true. All right. Well, what if they throw an equation at us? We'll start with something simple, something in slope-intercept form. F of x is equal to 6x minus 7. Is that a 1-to-1 function? Yeah, we know that's going to pass the horizontal line test. We know what it looks like. It's a line that's going up and to the right. We could graph it and verify that. So to find the inverse, what's f of x the same thing as? Y. So this equation is the same thing. Y equals 6x minus 7. Those two equations are exactly the same. Inverses swap the domain and the range, or swap x and y. So we're going to swap x and y. So swap x and y, and then solve for y. So add 7, x plus 7 equals 6y, divide by 6. 1/6 x plus 7 over 6 equals y. That's the inverse. So I'm going to write it in inverse function notation. F inverse of x, 1/6 x plus 7 over 6. We didn't have any restrictions on our domain to start with, so we don't really have to worry about that much here. We don't have to worry about that much anyway, but we do need to think about it sometimes. For this one, nothing to think about. There's no restriction on that domain anyway. Okay. Let's look at this one. Here's our function. F of x is equal to 2x plus 1 and x minus 1. And they tell us that x does not equal 1. We know that that's... Why are they telling us that? Because the fraction, the restriction on that function, the domain, x can't be 1, right? Or it wouldn't even be a function, right? If x were 1, then we get division by 0, and that doesn't work. So we can't do that. So this is a 1-to-1 function. Let's find the inverse of that. This one's a little more difficult because it's a fraction, so that's why we're doing it. They're not always going to be simple. Nice easy ones there. So we got y equals 2x plus 1 over x minus 1. Inverses swap x and y. So I'm going to put an x here, and everywhere there was an x on the other side, I'm going to put y. Now, I'm going to try to solve that. I'm going to try to get y by itself again. The problem that we're going to run into here is that y is in two different places. It's in the numerator and the denominator. So I'm going to get y out of the denominator first. And to get y out of the denominator, what operation do I have to do? what is this operation over here on the right anyway? It's a fraction, but that means it's really what? Dividing. The opposite of that would be multiplying. So if I multiply by y minus 1, that gets y out of the denominator there. I still got y over here. I've got xy minus x. Just doing distributive property there. So I still got y in two different places. So I got to do something about that. So when I'm trying to solve for y, I try to get all the y's together, right? And all the things that are not y's on the other side. So I'm going to move x, and I'm going to move 2y. Doing that all at the same time. One step to get that to happen. So xy minus 2y equals x plus 1. Now, what do both of those have? Y. So that's a common factor, right, between those? We think about factoring with greatest common factor. We could pull a y out to the front and leave x minus 2 in there. And now, what's going on between y and those parentheses? They're multiplying. The opposite of multiplying would be divide. I'm going to leave y where it's at, but I'm going to divide by x minus 2. There's y. There's x plus 1 and x minus 2. That's the inverse. So we write it in inverse notation. X plus 1 over x minus 2. What's the restriction we need to tell them about? X can't equal 2 in this case because the x minus 2 in the denominator. So if there's a restriction there, we need to tell them about it. This is our inverse with that restriction off to the side. That's really as tough as they get. You know, the fraction ones where you got to do that factoring trick there is as hard as they get. All right, with finding the inverses, they don't get much more difficult than that. All right, now let's look at verifying inverses. All right, so when you're verifying inverses, here's the statement that does all this. If f of x and f inverse of x are inverses, by that notation, we're saying they are, then you can verify that by doing function composition. This is why they're together in this chapter. And if you do function composition of two functions and they are inverses of each other, once you've simplified that function composition, you get x, no matter which direction you do that. Technically, to verify if two functions are inverses of one another, you're supposed to do both directions. That would be the I guess you'd say dummy-proof way of doing it. That if you did it one way, it's possible you made a mistake and it just happened to turn out to be x. If you do it the other direction and it still turns out to be x, probably didn't make a mistake. You're probably okay. So that's kind of the idea there. So let's look at a couple of functions and decide, are they inverses of one another? Are f of x and g of x inverses? I have no idea what letter we're on. H. F of x is 2x plus 3. G of x, 1/2, parentheses, x minus 3. So we need to do f composed with g of x. So that's taking g of x and replacing x in f of x. And work that out. Well, 2 times a half is 1. So that ends up being x minus 3 plus 3. What happens to the 3's? They cancel out. So that is x. That's one direction. If I go and do g composed with f of x, go the other direction. That's taking 1/2 x minus 3 and replacing x with the 2x plus 3. Inside those parentheses, that cancels. So that's 1/2 times 2x, which is x. That's verification in the other direction. So f of x, or f of x, and g of x are inverses. If you get anything other than plain x, they're not inverses. If you get negative x, that's not an inverse. If you get x plus 1, that's not an inverse. If you get 1 over x, that's not an inverse. It has to be plain x, 1x. That's what it's got to be for them to be inverses. All right. All right, let's look at verification with graphing using the same two. I'm going to show you this. Graphical verification, a little bit tougher to do sometimes, but sometimes can work out for you. With graphical verification, you're looking for a reflection across y equals x. Okay, so for our problem, if we graphed those two equations, same two equations from example H there, 2x plus 3, and then I'm going to graph 1/2 parentheses, was it x minus 3, is that right? Yeah, x minus 3. And then I'm going to graph the third equation. I'm going to graph y equals x so I can see what line I'm supposed to be reflecting across. So here's our first one. Here's the second one. Here comes y equals x. Okay. Notice how they reflect across that. One clue that if you're using graphical verification, that if the two lines cross or two equations cross, they will cross on that y equals x line. Okay. With linear ones, it's really easy to see. When you get to polynomials, it's a little tougher to see with graphical, depending on what the polynomial is. Algebraic verification is always stronger because it works. Graphical verification is nice unless your functions are really far apart. Like you got one that's way up in the second quadrant, one that's way down in the fourth quadrant. It's hard to see that sometimes. So graphical verification is not always the best, but it's definitely a valid thing to know out of that. So I'm going to paste that. There's the graph of graphical verification. So this was 1/2 x minus 3. This was 2x plus 3, and that's y equals x. That's what those things are on there. Graphical verification reflects across that y equals x line. If they don't do that, then they can't be inverses of one another. All right. Let's look at the next section. We're moving fast today. 6.3. Exponential exponential functions look like this. C a to the x. The c is the initial value. The a is your growth or decay factor. Growth or decay factor. All right. So exponential functions, you got an initial value. That's like if you were starting a savings account or something like that. That's something that's exponential in growth. Your first deposit is like you put $100 in the bank and you left it there for a while. The formula is a little different for that, but the idea of that initial value is the same. And then the growth factor is like your interest rate, kind of is the way that's going to work. All right, so let's look at some tables of values and decide if the ordered pairs are exponential. So is set of ordered pairs exponential. X and Y, so it's 0, 1, 2, 3, 4. And the Y values are 5, 10, 20, 40, and 80. Okay. So a couple of clues to decide if some things are exponential. The Y values should grow very quickly or they should shrink very quickly. If it's exponential, they grow fast. To go from 5 to 80 in 5 jumps is quite a bit, so that's pretty fast. The official verification would be take the ratio of your Y values. So 10 divided by 5, what does that equal? 2. Then take the next pair. 20 divided by 10. That's 2. 40 divided by 20. That's 2. 80 divided by 40. That's 2. Because of the division, the ratio of the Y values there is the same each time. This is exponential. This number, that ratio, what it reduced to every time is the growth factor. Why is it a growth factor, not a decay factor? It's positive, and what's happened to our Y values? They're going up. They're growing, right? So that's an indication. And so what's happening here is our initial amount, though, is coming from there. Or initial value. Why is that the initial value? Because the x is 0. That's it. That's the reason. Not because it's the first Y value given, but it's because that's where x is 0. So that's the reason that's our initial value. So we could write the equation for this exponential set by just saying f of x is equal to 5 times 2 to the x. And there's the equation for that exponential set. Then we could continue that pattern by using that equation. There. Sometimes they'll write that table sideways. Not my favorite way for them to do it, but it happens. Well, the numbers are dropping pretty quickly. So that should indicate maybe it's exponential. The test, though, would be what's 32? What's 32 divided by 16? Or, excuse me, 16 divided by 32. Dyslexia, sorry. Half. 8 divided by 16. Half. 4 divided by 8. Half. 2 divided by 4. Half. It's a half every time. That See our decay. Back. This is exponential decay. The function. What's the initial value? 16. Why not 32? Yeah, the x isn't 0 on 32. It's 16 is where the x is 0. So 16 times 1/2 to the x. And yes, put the 1/2 in parentheses. It's fairly important. All right. Let's recall some ideas about transformations. Say we had 2 to the x plus 4. What does that do to the graph of 2 to the x, the adding the 4 on the outside there? It's a shift up 4 units. And, on the graphing calculator, we could look at that and see it. Clear out this other stuff we were doing. 2 raised to the x. Here's the original one. This is what an exponential graph looks like. And then if I add 4 to that, 2 raised to the x plus 4. See, it raises it up 4 units. Very simple to see that. That's happening. So transformations are all the same here. Say we had f of x was 2 to the x minus 3. So the minus 3 is inside of the exponent there. Perfect. And if you're ever in doubt, graph it and look at it. What's this one doing? Doing a couple of things. 2 to the negative x minus 5. Going down 5 units. Okay, I agree with that. It's actually the y-axis. The negative is on the x. It's the y-axis that's reflecting across. If the negative were like down here in the front, like that, that would be across the x-axis. That's a reflection across the y-axis for that one. Okay. Be able to recognize those things. That's one of the things that there's usually one of those on the final. It's a pretty easy thing if you remember it. And so try to get those every now and then. All right, so let's get to the meat of this lesson, this section, the solving exponential equations. Two to the x plus 5 is 2 to the 8th. What's this number down here called? Does anybody know? Talking about exponential things. It's called the base. Like if you had 2 squared, it's the base of a 2 with the exponent there. So these are the bases. Anytime the bases are the same, then you can just drop them and have the equation x plus 5 is equal to 8 to solve. And we'll talk about later on the math that's making that happen, but basically all you need to know is if the bases are the same, drop them. And then solve that easy equation there. is equal to 3. And where they're obviously they're not going to make it that easy on you. They might throw that out there. 2 to the x plus 1 is equal to 16. And the idea is that you think, okay, if I can get the bases the same, then I can get an easy equation to work. So what is 16 in the terms of 2 as a base? Let's see. 16 breaks down into 8 and 2. 4 and 2. How many 2's is that? It's 4. So 2 to the 4th power is what? And so now the bases are the same. So I can drop them and say x plus 1 is equal to 4. And solve that. And there x equals 3 again. What if it's 3 to the 5x is equal to 81? So really what you're looking for here is okay, which one has a prime number as a base? 3, right? So 81, I must be able to write 81 as 3 to the something. What would it be? So 9 and 9. 3 to the 4th. And then we can drop the 3's because the bases are the same. And now we got a one-step equation to solve. A fraction answer, and that's quite okay. And then you get one like this where, I said on H, you kind of want to look for that prime number at the as the base, and neither of these is a prime number at the base. So I'm thinking, okay, well, what prime number works with 2 and 8? I mean, 4 and 8. Sorry, I just gave it 2, obviously. So 4 is actually 2 and 2, right? So that's 2 squared. Then 8 is 4 and 2, 3 2's. So that's 2 cubed, right? What happens with these exponents? What operation do you do with them? Remember some exponent rules from. Say it again. Multiply them. Yeah, that's right. Yeah, it's like distributive property. 2 times x or 2 times 2x would be 4x minus 1, and this would be 3x, and you can drop the bases because they're the same now. And now we got a nice equation. It's not too difficult to solve. It would be -2. Thank you. I'm going to work a problem right tonight without you guys. Correct. I appreciate it. And then solve it. So subtract 4x. -2 equals -1x. Divide. This is 2. We got to think in terms of exponentials. That's what we're trying to do here. Think in terms of exponential representations of numbers. Here's an interesting one. Nine to the 2x, 1 over 27. So a lot of times the fraction is not the one you want to start with because it's always the more complicated looking one. Think about 9. 9's not a prime number. What prime number does 9 work with? 3, right? So it's 3 squared. And then you got to think, okay, well, that 27 is on the bottom. So 27, though, is 9 times 3, and 3 and 3. So it's really 1 over 3 to the third. That's what's going on there. But what exponent rule allows me to move that from the bottom up to the top? So that it's 3 to the 4x equals 3 to the, yeah, that's right, negative 3. Change the sign, and you can move it from the bottom to the top. So now we got the bases the same, and it's a pretty easy problem. Four to the 3x squared equals 8x. 8 to the x. Sorry. So we've dealt with 4 and 8 before, so we know we're going for what as the base? 2. Okay? So that'd be 2 squared. So that's 2 to the 6x squared. And then 8 is 2 to the third. So that's 2 to the 3x. So now the bases are the same. So I drop the bases. So I got 6x squared equals 3x. It's got an x squared in it. Nope. Because it's got a plain x in it too. If it was just a number over there, yeah, square root's probably the way. But it's got the plain x over here too. So can't divide by x because x might be 0. If x is 0, I can't divide by it. Remember, that's undefined. So we don't know what x is, so we can't divide by an x. So when we're doing quadratics, what did we get it equal to? 0. So subtract 3x. And then you got a quadratic that's equal to 0. So you got options about solving it. One of the ways would be factoring. Another way would be quadratic formula. I'll use factoring here because I know 3x is the common factor, leaving x minus 1. Then you set each factor equal to 0. And lo and behold, x was 0 in one of those. So that's a good thing we didn't subtract or didn't divide by it. That's 2x minus 1. And then divide by 3. 0 divided by 3 is 0. And then add 1. X is 1/2. 2 answers there. You could plug those back in to the original, make sure they work. They do. But 2 answers there because we had x squared to begin with. But whatever the degree is there, you're going to get that many answers. Okay. Another thing that's introduced in this section is the exponential number, e. It's the number that came up. It's kind of like pi. It comes up enough that it needed its own representative because you didn't want to write the big long decimal that goes along with it. Because pi's never ending, e never ends either. But it's about, when you take e to the first power, it's about 2.71 is about what that number is. It's just a number. We're going to leave it as e right now and work with it from there because we're dealing with exponential equations. exponential number would make sense that it would be in here. So L e to the 2x equals e to the x minus 5. That's just a number. They try to make it look like it's really confusing, and it's not. It's the base is e. If it's the same base on both sides, get rid of it and just do the easy problem. And x is -5 in this case. And they try to get a little fancy with us here and go this route. Absolutely. That's the exponent rule is add. So e to the x squared plus 7x equals e to the -12. And then we know, oh, well, the bases are the same, so get rid of them. And we have x squared plus 7x equals -12. And we got another quadratic to work on. So how do we solve that? Can't take square roots because it's got the plain x term in it. So we got to get it equal to 0 first. I'm going to add 12. And then now I've got a, b, and c. I could do quadratic formula if I wanted to. Or I could factor it. 12 and 7. 4 and 3. So that's x plus 4. X plus 3. And then solve those. I get x equals -4. X equals -3. And that's section 6.3. One more section. I'm getting half of chapter 6 tonight, so second half really stems off of everything we've done on the first half. So a lot of stuff tonight, but kind of broad. Savannah, you got a question, or you just trying to stay awake? I got you. I understand. I'm trying to talk fast and get you guys out of here. Logarithmic functions, fun stuff. I know some of you high school guys, you're probably thinking, okay, we're doing this in algebra 2, right? Yeah, I mean, college algebra follows same stuff you do in algebra 2. It's not much different. So I always tell our students at my high school, if you can survive my algebra 2 class, you can take my college algebra class next year, and you're going to see the same stuff, just a little deeper. And I'm probably not going to be as forgiving when you do things late in that class, but that's another thing. But logarithms are exponents. That's what you got to remember. A logarithm is an exponent. A logarithm is an exponent. Logarithms are exponents. That's what you got to know. Okay, so when we go to rewrite logs as exponentials, that's what we're going to do. Mathematicians are really, really good at taking something they don't know how to do and rearranging it until it looks like something they do know how to do. That's what we do as mathematicians. We take problems and say, that looks tough. Can I make it look like something I do know how to do? And we do that so that then we have skills in order to solve some things we're familiar with. So if we can rearrange something into something we're familiar with, it makes it easier. So here, to understand logs, if we can rearrange them into exponentials, we just got through doing some exponentials, and I don't think any of those equations we did with exponentials were very hard. So if we can rearrange them that way, it can help us understand them. So we're going to rewrite some logs as exponentials. So we'll start with a pretty simple one, log base 3 of x. And that's how that's written. Y equals log base 3 of x. So if you can read it correctly, it almost spills the beans as to how you're supposed to do it, okay? The way it works, whatever the base is for the log, that's the base for the exponential, okay? A logarithm is an exponent. So in math, is means equals, right? Always since 8th grade math, when they're translating equations out of words into equations, we tell them if you see the word is, that means put an equal sign. So this logarithm is an exponent. So the exponent is the y. Okay, so it's 3 to the y. And then the only thing left that we hadn't used yet is the x. Okay. Whatever the base is the base for the exponential. Whatever the log is equal to is the exponent. And then whatever's inside of that log, that's what your exponential is equal to. Log base 2 of x equals 3. Well, what's the base? 2. What's it equal to? 3. What's inside the log? X. And that would merit an equation that we could solve, right? 2 to the third power. We know that's 8. X would be 8. So that's not what we're after right here, but it's kind of the idea where we're going. Log base 5 of y is equal to x. What's the base? What's the exponent on that base? X, because that's what the log is equal to. What's that equal? All right, here's we're going to throw you for a loop. Natural log of x equals y. All right, here's what we got to have a definition for. Natural log, ln. It's called natural. I don't know why the n's not first, but ln, natural log is what that stands for, is log base e. So anytime you see ln, natural log, think, oh, that's log base e. The base is e. That's what you got to think. So if the base is e, this is e with what exponent? Y. E to the y equals all right. So here they wrote log. They didn't write a base down there. Does anybody know what number system, what base number system we live in? Like, or do we live in base 6, base 10, base 2? Base 10 is the number system. The reason it's base 10 is because we have a ones digit, a tens digit, a hundreds digit, thousands. They're all bases of 10 when we count things. Now, if you look at an analog clock like that one up there, that's written in, that clock is actually base 6. If you go through the motions of doing that. So this is base, anytime they don't put that there, it's a base 10. Plain log is base 10. Okay. ln is base e. Any other base, they're going to write. Okay. So that's what's weird about this. So that's 10 to the third equals x plus 4. And, that would build us an equation that we could actually solve. We could do some work and solve that. 10 to the third is 1,000. Minus 4 would be 996. We could get x out of that. So being able to rewrite a logarithmic equation as an exponential equation can make it easy to solve. So that's kind of where we're headed with this, is what I'm kind of trying to model for you. I don't know if I'm doing a good job or not, but let's go the other direction. And let's write the exponential as a log. 3 to the x is equal to 27. Okay? So when we're doing this, what's the base in that problem? 3. So it's going to be log base 3. What's the exponent in that equation? So that's what it's going to be equal to. So 27, it's got to go there. Let's do 5 to the x plus 1 equals y. What's the base? 5. So we're going to write log base 5. What's the exponent? So that's got to be what it's equal to. What goes in this blank space here? One of those in there. What's the base? Yeah, it's base 10, so we're just going to write log of y equals minus 4. All right, what's the log on this one? Log base 5 of 625 equals x. Pretty simple to rewrite. Let's throw one of those weird ones in there again. E to the square root of 2 equals y. Excuse me. What's our log? LN, natural log of equals 2. I got that. That's cake right there. Easy stuff. Okay, so let's use that to work out evaluate some logs without a calculator. Spell calculators. Yeah. All right. Log base 2 of 16. Now, some of you may be a little bit better at this than others. I want to take you through the process of, okay, well, what if I don't know what I'm doing here? How can I get there? The trick here is thinking, okay, well, 2 is the base, so I'm looking for what 2 to what power gives me 16. That's what I'm looking for. The way to think about that, or my way of thinking about that, is I'm just going to set that thing equal to x, and I'm going to rewrite it as an exponential equation, because we've done those already. So this would be 2 to the x is equal to 16. And we've done a problem almost exactly like that. 16 we know is 8 and 2, and 8 is 4 and 2, and that's 2 and 2. So that would be 2 to the 4th. So we get this equation, 2 to the x equals 2 to the 4th. And that allows us to say, oh, the bases are the same, drop them, x equals 4. So that means log base 2 of 16 is equal to 4. That's doing it without a calculator. And that's what we're trying to think about doing here. I'm going to show you that your calculator will do this too. Don't get me wrong. I'm not expecting you to do everything without a calculator. On the calculator, to get it to verify that, just to make sure you did it right, you can use the log base function, and that's under the math menu. And I go over to number. Oh, not number. Under math, press up. And log base. If you're using the newest graphing calculator, if you're using an 84 or 84 plus, it should do this. If you're using an 83, we'll have to talk about a change of base formula for you. Is anybody using an 83 in here? I'm trying to glance. I see mostly 84s because they got two holes at the top. Yeah, 84, 84, 84s. Okay, everybody's got 84s. So when you hit that log base, and to get there again, you're going math, and then just press the up arrow, and you'll see it down at the bottom. Hit enter, and it gives you a blank spot for the base of the log, base 2, and then you put in the number 16, and then it'll crank out the result there. That's nice. You kind of want to be able to think about them without the calculator. And I know it's not something that many of you are going to spend a whole lot of time doing. If you did log base 4 of 1 over 64, if you're going to evaluate that, you want to think, okay, well, it's log base 4 of 1 over 64 is equal to x. So that's 4 to the x equals 1 over 64. Now I think, okay, that 4 is not prime. So I can break it down to 2 and 2. So that's 2 to the 2x. And then what about 64? It's 8 and 8. 8 is 4 and 2. 2 and 2. And this 8 does the same thing. 1, 2, 3, 4, 5, 6. And then my equation that I have is 2 to the x, or 2x equals 6. So x is equal to 3. Right? But it's not that. It's actually negative 6 because it was a fraction. You just change the sign. Not much else. I mean, there's no magic involved there. The thing you got to be careful with using the calculator to do that is making sure your fraction is in parentheses there. You don't, mess up and forget to put it as a fraction. But it says do it without one, but I'm not, just crazy going to make you do a ton of them without it. Let's talk about functions with logarithms. F of x equals log base a of x, just a basic log function. Not so much solving equations here, but just looking at log functions as in terms of graphs. The domain is from 0 to infinity for any log, no matter what the base is. Now, log base, dealing with that. The range, why put that in parentheses? Be from negative infinity to positive infinity. So, key things to note about that. We can never take the log of 0 for a negative number. We can never, no matter what the base is, we can never take the log of 0 or a negative number. Never going to be able to do that because you can't raise a number to a power and then it make the number magically negative. It's not going to happen. No number to a power is ever going to turn a number into 0 because the 0 exponent turns it to 1. A negative exponent makes it a fraction, right? Just moves it to the bottom. So it's never going to turn it into 0, and it's never going to change the sign of it out of that. So let's look at some, and we're going to state the domain of the log function. log base 2 of x plus 3. I don't know what letter we on, guys. Is that M? M. All right. No matter what this base is, that doesn't matter at all. You can put anything there. Okay. We're going to take this, whatever we're taking the log of, and we're going to set it greater than 0. Because we cannot take the log of a negative number, so we need it to be positive. We can also not take the log of 0. So we just set it greater than 0, and it takes care of that. And if we solve that, we're going to find our domain. Subtract 3. X is greater than negative 3. So our domain in set notation, x such that x is greater than negative 3. In interval notation, from negative 3 to infinity. Range of that would still be from negative infinity to positive infinity. It's always going to be the same with those. Right. Let's look at an exceptional one. So let's say we had f of x or y, it doesn't matter, equals log base 5 of 1 plus x over 1 minus x. That's scary stuff. It's a fraction in there. It's close to Halloween, so. What we've got to do is set up 1 plus x over 1 minus x and put it greater than 0. Now, here's where some things get crazy. We've got to think, okay, what could make this not work? What x value could screw this whole thing up? 1. X being 1 is going to mess things up. So what other values would give me x's? What values would give me 0 as this? Negative 1 would also, because negative 1 plus x or plus 1 is equal to 0. So that would give me something equal to 0 there. So I know my spots that I need to check around are at negative 1 and positive 1. Those are the boundaries that we're going to check. Positive 1 and negative 1. Okay? That positive 1 is coming from the denominator. The same way we'd normally find a domain. X can't be positive 1. We know that because the 1 minus x on the denominator. The negative 1 comes from setting the top of the fraction x 1 plus x. If we set that greater than 0, work it out, you're going to get x is greater than negative 1. So we've got some intervals that we need to check. And I've drawn a number line here and just put those two numbers on it, negative 1 and positive 1. We need to check a value in each interval. So we pick a number that's in this interval. So less than negative 1, negative 2 fits into that. So if I check negative 2 in this inequality, 1 plus negative 2 over 1 minus negative 2. We want to know, is that greater than 0? Well, that'd be negative 1 over 3. Is negative 1 over 3 greater than 0? Oh, that's false. So this area, that whole area is false. Just by checking 1, we know that there are no pieces of the domain that are less than negative 1. And then we want to check a number that's between negative 1 and positive 1. 0 would be the great number to check between there. You could check negative 1/8 if you wanted to. I don't know why you'd want to. You could. But we're going to check 0. So 1 plus 0 over 1 minus 0. Is that greater than 0? So that's 1. Is 1 greater than 0? That's true. That's true in that area. It could also be true for x is greater than 1. Okay, so I'm going to check a number over here. I'm going to check positive 2. And plug that in. 2 plus, or 1 plus 2 over 1 minus 2. And I'm checking, is that greater than 0? That's 3 over negative 1. Is that greater than 0? No, that's false. So then we report for our domain the only true areas. So from -1 to +1. That's our domain. You get your places, your boundaries. You get those from the numerator set equal to 0 and the denominator set equal to 0. If it's a fraction inside of there. Numerator set equal to 0, denominator set equal to 0. All right, let's look at another one here. F of x equals log base pumpkin. That's a pumpkin, isn't it? Jack-o'-lantern. So log base pumpkin, doesn't matter what the base is. We can do the work no matter what. Absolute value of x plus 2. Ooh. He put an absolute value in there, and I don't know what an absolute value does. Doesn't matter what the base is. I chose pumpkin, jack-o'-lantern, because it doesn't matter. The work is the same. You don't have to. You can put a number in there. If it intimidates you with my artistic ability, I'm sorry. If that gets me an A in art class, oh Lord. Did make A's in art class, but anyway, it wasn't for my jack-o'-lantern drawing. All right, so let's set the absolute value of x plus 2 greater than 0. So we got to remember how to solve an absolute value inequality. And the way I've always taught it is land of or. The L is a less than. It's an and problem. G is a greater than. It's an or problem. That's the way I've taught that for years. So I'm going to set up x plus 2 is greater than 0, or x plus 2 is less than. And you're supposed to change the sign, but 0 doesn't have a sign, so we just put 0 there. And solve each of those, and we get the inequalities for the domain. So x is greater than -2, or x is less than -2. It's two intervals there. So we go from -infinity to -2, union from -2 to positive infinity. That's our domain. I'm just trying to show you these things because you're going to see them later. All right. So there's some stuff with domain with logarithmic functions. Let's look at actually solving some logarithmic equations. 1, 2, 3, 4, 5, 6, 7, 8. 8 problems, and then we'll get out of here. I don't know if we can do it, but we're going to try. All right. I don't know what letter we're on either. What letter was that? I didn't even write a letter on that one, did I? I was too busy drawing my pumpkin. That was example donut. Does it not look like a donut? It looks like a donut. Example P. All right. Log base 3 of 4x minus 7 is equal to 2. That's a log base problem. I think it'd be easier for me to rewrite it as an exponential. How do I rewrite that as an exponential? The base is 3. Yeah. And what's 3 squared? And then we're back in 7th grade math. Yeah. Yeah. Fun. Easy stuff right there. What if they put the x in the log base? Log base x of 64 equals 3. Oh, it's just x to the third equals 64. What to the third power gives me 64? Now let's think of our cubes. 2 cubed is 8. 3 cubed is 27. Oh, I forgot 1 cubed is 1. What's 4 cubed? Oh, it's 64. So x is 4. That's nice. Say we had log base 3 of 3 to the 6x equals 42. I'm going to show you a trick on this one. Is there a trick? There's no need for a trick. Yeah, that's equal to 3 to the 6x. And then the bases go away, and it's 42 equals 6x. No trick involved. 7 is x. This stuff is easy, isn't it? Let's see if we can make it harder. 81 to the x equals 27. That's not a logarithmic equation. Does it need to be? No, we already work problems like this. How do we work it? We try to get what the same? The base the same. So I'm thinking 27 and 81 have 9 in common, but 9 is not a prime number. What prime number do they have in common? 3. So 81 is actually 3 to the 4th power. 27 is 3 to the 3rd power. So that's 3 to the 4x equals 3 to the 3rd. Now, we've been doing this magical hand waving thing where the bases go away. The actual math that makes those bases go away is doing this. That this log base 3 on each side cancels that out. And that's how we get 4x equals 3. That's actually the math that's making it happen. And the base on the log is the same as the base from the problem. That's what cancels it. They cancel each other out. And that's some magic math stuff. So x is equal to 3/4 in this case. Now, why is that important? Well, what if it's not nice numbers like that was, where it's 81 and 27? They all work out to be nice numbers with the same base. Okay. If that's the case in point, example something other, t, 3 to the 5x is equal to 24. They kind of screw things up when they do that. It's not easy math anymore. It's 3 to a power, and then 24 doesn't turn into 3 to a power. Not nicely, anyway. It's not 3 cubed or 3 squared. So what you want to do is think, okay, well, I'm going to get rid of that base of a 3 so I can get that x out of the exponent so I can do some work. So if I do log base 3 of 3 to the 5x, that'll get rid of the 3. But whatever I do on one side of the equation, I got to do the same thing over here. These cancel. The other side, they don't cancel. Log base 3 of 24 is just a number. It's an ugly decimal number, so we're not going to change it to it yet. Okay? Log base 3 of 24 is a number. That's what you got to realize. How do I get x by itself over there? Yeah, just divide by 5. Like that. And then our exact solution is log base 3 of 24 divided by 5. The decimal approximation for that, we want to be able to get that as well. So we're going to use that log base trick on our calculator. Math. Log base 3 of 24. And then I'm dividing that by 5. 0. We'll go 3 decimal places. 579. excuse me. 2 to the 3x plus 1 is equal to 15. Well, we should have made that a 16. It'd have been easy. They made it a 15. So what do I do? What log base can I use to get rid of that 2? What log base should those be? What log base is going to get rid of a 2 as a base? Log base 2. Whatever the base is on your exponential part, that's the base for your log you're going to use. That will cancel those out. That's what you need to grab onto here. That's going to cancel that out. And then log base 2 of 15 is just this ugly decimal number. Just got to remember that. And then it's 3x plus 1. Log base 2 of 15. Subtract 1. It's getting uglier. I'm going to put that in parentheses there. I think it makes it clearer that it's not log base 2 of 14. Divide everything by 3. So log base 2, 15, minus 1, all divided by 3. And then we want to get a decimal approximation for that. Fun times. Math. Log base 2 of 15 and subtract 1. Divide that answer by 3. 969. Oops. 0.969. Getting exact and decimal approximations for those. Okay. We can also use, since we're in that chapter about the inverses, last thing here, we're done for the night, is find the inverse of a function. Uses the same exact skills as solving did. UV. F of x, natural log x minus 3. That's a y. What does inverse do? Yeah, swap spaces with x and y. And then we want to get y by itself, so we don't need it inside of a log. So we can rewrite this as an exponential. What base is that natural log? What's that? E. So that's as e to the x is equal to y minus 3. And what do you know? It's pretty easy to get y by itself now. E to the x plus 3 equals y. So f inverse of x is e to the x plus 3. One more. The different logs involved. F of x, log base 4, x plus 5. We're going to find the inverse. So we'll go x, log base 4 of y plus 5. Rewrite it as an exponential. What's the base? 4. The x equals y plus 5. Subtract 5. Y is equal to 4 to the x minus 5. Equates to the inverse function. 4 to the x minus 5. All right. Good times. You got a quiz up on Canvas. I'm going to write some suggested problems from the book. The next week we'll have lecture again, finish up chapter 6, and then the next week you'll have an exam on November the 13th, and then we'll have class the Monday before Thanksgiving. That's November 20th. November 27th, we'll also have class. Your last regular exam will be December the 4th, and then your final exam will be December the 11th. And we'll go from there. And that'll be the end of the semester. So 1, 2, 3, 4, 5. 5 class meetings and a final. We'll be there. Moving fast. All right, page 4. You guys have a great night. If you want to stick around and write this down, you can. Or you can catch it from the video on YouTube.